We've spent quite a bit of time now looking at multi-force problems in one dimension, multi-force problems all on the horizontal axis. Things on the ground, right? You're pulling a wagon to the right, or you're pulling a car to the left, and there's friction to the right, or whatever the case may be. What I want to look at today is multi-force problems, but vertical multi-force problems. Now, that could take a number of different forms. One form that it could take is somebody standing on an elevator. This is the floor of the elevator. The person stands on this elevator. What happens? What forces act on this person as this person is on the floor of the elevator? Tell me one force that's always acting on this person. Gravity. Gravity is going to be acting down. That doesn't matter whether I draw gravity acting down right here or whether I draw it acting down right here. It doesn't make any difference. It's acting down. Now, what other force would act on this person in the elevator? There's one more force that's important here. If only gravity acts on this person in the elevator, this person is going to free fall to their death at 9.81 meters per second squared. There must be something countering gravity if we don't want this person to plunge to their death in this elevator shaft. What is it? Yeah, the force of the elevator, the force of the floor pushing up. We're going to call that the normal force, right? We're going to call that Fn. Now, if the elevator is accelerating downward, you're in an elevator on the 100th floor of a building, and you start accelerating downward, which is going to be bigger, gravity or the normal force? Gravity, right? Otherwise, you're not going to accelerate downward, right? If normal force is bigger, you're going to accelerate upward. So what happens here? We accelerate down. And the rate of acceleration downward, it will be bigger than 9.81 meters per second squared. We know that because, look, if you have gravity acting down, and only gravity, that's going to cause 9.81, not greater than 9.81, but what should I have said? Not greater than 9.81, but less than 9.81, right? Because if you have an acceleration just caused by gravity, then it's going to be downward at 9.81 meters per second squared. But if there's a normal force countering that, but it's smaller than gravity, you still accelerate down, but it can't be as much as it would be if there wasn't a normal force acting up. So the rate is going to be somewhere between 0 and 9.81. What if we have a situation where the person is in the elevator, but accelerating upward? You're on the ground, and it's that moment when you feel your stomach go down. You feel heavy. Okay, what happens then? Gravity acts down still. Normal force acts up, right? How does the normal force compare to gravity now when you're accelerating upward? It's bigger, somebody said, yeah. The normal force is bigger than gravity. Now, what's the rate of acceleration? We have no way of predicting this. Okay, the acceleration could be 1.0 meters per second squared upward, or it could be 50 meters per second squared upward. Depends on how big the normal force is. We can't say that it's less than or bigger than a certain number. What if this elevator is moving at a constant velocity? And that's what happens, right? Elevators start accelerating initially, but then pretty quickly they start moving at a constant velocity. What's the force of gravity going to look like if it's moving at a constant velocity as compared to the normal force? Here's gravity acting down. Tell me when to stop drawing the normal force. Tell me when to stop. Right now? If it's moving at a constant velocity, the normal force is bigger than gravity. If the normal force is bigger than gravity, doesn't it accelerate upward? Should it be smaller? Because then it accelerates downward. But wait a second. If the normal force and gravity are the same value, doesn't that mean it's just going to stop? No, if the elevator is moving, if the elevator is already moving, and those two forces balance each other, what's going to happen to it? It's going to keep moving at a constant speed, in a straight line at a constant speed. So in this case, we'd actually say the acceleration is 0 meters per second squared. It doesn't mean it's not moving, it just means it's not accelerating. It's going at a constant velocity. Now, I've got 3 diagrams drawn here for people in an elevator. We could easily extend this to the same problem effectively, but a slightly different context. So let's say You're lifting a bucket of water upwards. Here's your bucket of water that you're lifting upwards. Okay, let's say that we want that bucket to accelerate upward. Here's the rope that we're pulling it up with. If we want it to accelerate upward, then we know that we have to have, well, a force of gravity acting down. What pulls up on it? What's the rope? Let's call that the normal force, the force of the rope. Let's call that the normal force. In that case, should have moved that over here, actually. If it's accelerating upward, that's an odd-shaped bucket, I know, then the normal force is going to be greater than the force of gravity. I don't care what provides the normal force. I don't care whether it's the floor that provides the normal force, or whether it's a rope that provides the normal force, or a chain, or a cable, or whatever, a track on a roller coaster that provides the normal force. In the end, whatever it is that counters that gravity is going to be what we're going to call the normal force. So, you get a problem like this, or like this, or like this, or like this, where it's a rope pulling it up. We're going to do the same thing. Move to step 2. Step 2 is F net is equal to the sum of the forces. And for all of these vertical problems, the sum of the forces will simply be Fg plus Fn. We solve for whatever variable we're looking for. Let's take a look at an example from your notes. Example number 3 says a 73-kilogram man stands in an elevator that accelerates downward at a rate of 2.0 meters per second squared. I'm gonna draw attention to this, actually. How come? What mistake do you think I might make on this if I don't be careful, if I'm not careful? Yeah? Yes. Yes, we need to make 2 a negative value when we sub it into the equation. What's the force of the elevator floor pushing up on him? Let's draw the guy in the elevator. Now, I could draw, I suppose, the whole elevator around him, but it doesn't really matter, because in the end, it's the floor that pushes on him, right? Not the walls or the ceiling of the elevator. So we're fine just drawing the floor. Gravity acts down. The normal force acts up. Is the normal force bigger or smaller than gravity here? This elevator accelerates down. Which is bigger, gravity or the normal force? Sorry? Gravity. The downward force has to be bigger, otherwise it wouldn't accelerate down. So I'm going to draw the normal force up, but smaller than gravity. Now I'm going to say step 2, F net is equal to the sum of the forces, Fg plus Fn. And then I'm going to say step 3, replace F net with M times A, exactly the same as I did for all my homework questions. MA is equal to Fg plus Fn. Now I start subbing in some values here in step 4. M is 73 kilograms. A is negative 2.0 meters per second squared. Negative because it's downward. Fg is 73 times 9.81. But we're going to make that negative because gravity is down. I'm reminded of that because of my diagram. Plus Fn. That's really what we're solving for here, right? The normal force, which is the force of the floor, pushing up at 90 degrees to the guy. Okay, 73 times 2 is negative 146. 73 times 9.81, I believe, is negative 6. No, I don't remember. I don't remember what it is. 7. Thank you. It is negative 716.13 newtons. Okay, don't forget the negative because it's acting downwards. Plus Fn. Now, let's take the 716 over to the other side. How are we going to do that? Add, subtract, multiply, divide? Brayden, how do you want to take that 716 over there? Yeah, it's negative on the right side. Take it over by adding. We're going to say negative 146. Negative 146 plus 716.13 gives me a value of 570.13. Now, how many digits should this be? We got to be conscious of that now because it counts now, right? Final answer should be 2 digits. It's going to be 5.7 times 10 to the 2 newtons. How hard does this floor have to push? 5.7 times 10 to the 2 newtons. Okay, if you're an engineer designing an elevator, you better make sure that this floor can withstand 5.7 times 10 to the 2 newtons. In fact, you better make sure that it can withstand more, because when you accelerate upward, the normal force is bigger, right? What's the man's actual weight? Don't overanalyze this one. What did we define actual weight as a couple days ago? You're going to get a question on your final exam in a different context that asks for actual weight. And some of you are going to say the actual weight of a man is 73 kilograms. You will be wrong if you say it's 73. His actual weight is not 73 kilograms. His mass is 73 kilograms. Some of you are going to say his actual weight is 5.7 times 10 to the 2 newtons. That would be wrong. That's not weight, that's the normal force. His actual weight is defined as his force of gravity. The force of gravity, we figured out a minute ago, is 716.13. Right? The force of gravity is m times g, which is 73 times negative 9.81. So I say m times g, usually we say m times a, where a is negative 9.81. That works out to be negative 716, or negative 7.2 times 10 to the 2 newtons. Now, if you left off that negative, I can live with that. We usually express gravity as a positive value. Sorry, we usually express weight as a positive value, although technically it is negative because it is the force of gravity acting. That's all there is to that. On that exam question, do not say 73. On that exam question, do not say 5.7 times 10 to the 2. The actual weight is simply the force of gravity. And you don't need to do anything crazy to find that. You just multiply m times a. Now, remember what we said that first day of this unit, or the first day of these multi-force problems when we were talking about weight, though? Weight and normal force. We said what you feel as your weight is not really your weight. Your weight is gravity. You don't feel gravity. When you jump out of an airplane in free fall, you feel weightless. Your weight is still 7.2 times 10 to the 2, but you don't feel 7.2 times 10 to the 2. You feel weightless. What is it that you feel as weight or perceive as weight? It's not gravity acting down. It's a normal force acting on you. So question C, where it says, what's the man's apparent weight? What's the answer? It's an even quicker answer than it was in question B. What is it, Parker? How heavy do you feel here? My normal force. I feel like I weigh 5.7 times 10 to the 2 newtons. So I do weigh 7.2. I feel like I weigh 5.7. I feel lighter. You ever been in the elevator at the top of that 100th floor building or 50th floor building, and you accelerate downward, and for that brief moment while you're accelerating, you feel lighter? You feel lighter because the normal force doesn't push on you as hard. Your weight is still the same. It's still 7.2. But you feel like you're 5.7 for that time while you accelerate because the normal force is less. What I'd like you to do right now is take a look at the worksheet that I handed out to you a few minutes ago. The front side of worksheet number 12, specifically questions 1 to 4 on worksheet number 12. All right. By special request, we're going to go over the first question here. Calculate the normal force on the person in the elevator. By the way, the normal force on the person in the elevator is exactly the same as the force of the floor pushing up. Right? Number 1 and number 2 are going to have different answers, but we're looking for the same thing. We're looking for Fn in both of those cases. Let's draw a free body diagram first. Okay, it's accelerating upward, but we still have gravity acting down. The normal force, however, has to be bigger than gravity because it accelerates upward. If it accelerates downward, then the normal force is equal to gravity. If it moves at a constant velocity, if it accelerates downward, then normal force is smaller than gravity. If it's at a constant velocity, the two are going to be equal. Okay, let's set it up now. F net is equal to the sum of the forces. Step 2, Fn plus Fg. Step 3, m times a is equal to the sum of the forces. Fn plus Fg. And finally, step 4 is subbing new numbers. The mass here is 60 kilograms. The acceleration is 2. It's positive 2 because it's upwards. The normal force is what we're looking for here. Fg is 60 times negative 9.81 meters per second squared. Gravity is downward, so we're going to make it negative. 60 times 2 is 120. 60 times negative 9.81 is negative 58. I want to say 58.86. Is that right? Negative 588.6. Yes. Thank you. Now, we're going to take that 588.6 over to the other side by adding. Yeah, somebody said it. By adding. So when we do that, Fn becomes equal to, what, 708.2 newtons? Right, it's negative on the right side. Take it over to the other side by adding. So it's 120 plus 588 gives me 708.6, which we're going to round to 3 digits, or 709 newtons is our answer. Question 2, I'm not going to do this one. It's very, very much like question number 1. What's the fundamental difference between question 2 and question 1? Yeah, it's accelerating downward. So you're going to make that acceleration when you sub it in negative 2.0 meters per second squared. Now the free body diagram will look a little bit different as well. Gravity is bigger than the normal force here, right? Because it accelerates downward. Okay, I want to show you one more quick little thing in case any of you are struggling on this. Relates to question number 3. Calculate the apparent weight of the person in the elevator. What am I looking for there for apparent weight? What variable am I solving for? Normal force, same as I was in question number 2 and question number 1. What do you got to watch out for in question number 3? It's a constant velocity of 3 meters per second squared. Gravity acts down, the normal force acts up, and those two values are going to be the same value, right? Fn and Fg are going to be the same. What does that make the acceleration? Not 3. Don't plug in 3 for the acceleration. Rather, you're going to plug in what, Julian? You're going to plug in 0 for the acceleration, right? So moving at a constant velocity. I don't care what value the velocity is, 3 or 30 or 300. The acceleration is 0. Okay, remember that, and then solve it just like you did the other questions, subbing in 0 for the acceleration.